Section 4 covers the analog to digital converter, or ADC. Since most MSP430 projects measure and or control things in the real analog world, the device needs to be able to monitor what's happening out there. One channel of the 10-bit ADC is connected to an internal temperature sensor. You'll use that sensor to monitor the temperature of the MSP430 and experiment with the ADC.
The ADC-10, or the analog to digital 10-bit analog to digital converter on the value line parts, is very fast and very flexible. 10 bits, 8 channels, successive approximation on most of the parts, as many as 6 external channels, a VCC, and internal temperature sensing. 200 kilosamples per second plus a little bit. It also has a selectable conversion clock. You can run it off any of the available clocks and the ADC-10 oscillator, which is about a 5 megahertz oscillator inside the device. There is a auto scan that will allow you to do a single measurement, a sequence of measurements on any of the channels, to allow you to repeat that single measurement and to repeat that sequence of measurements if you like. There are programmable internal and external references available. You can trigger the ADC off of the timer A. The ADC is also interrupt capable. When it completes its measurement or completes its series of measurements, it will send an interrupt to the processor. The ADC also has the data transfer controller, which is like a DMA but very simple. And the ADC will also automatically power down after a certain period of time not being used. Taking a look at the ADC-10 sample timing, the timing of the ADC is such that you have complete control of it. You can turn on the reference separately, you start the conversion separately, you read the end of the conversion separately. This way you can control both the timing and the power consumption of the device. When you turn on the reference voltage, the reference must settle for about 30 microseconds before you make the conversion. There's a selectable hold time available in the ADC-10, and once you've given the conversion start, there's a 13 clock conversion process, since this is a successive approximation converter. The clock sources, you have the A clock, M clock, and SM clock available, same 3 that you saw earlier, and the ADC-10 oscillator, which runs in the 5 megahertz range. Having the auto scan on the MSP430 device is a important feature for lowering the power consumption and the amount of code that has to be running at any given time. You can see from the code example on the left where we would have to switch channels and go between each and every one of the input channels making the measurement. Instead, we allow the auto scan and the direct transfer controller to do all of this for us once we've programmed it. It will load the information into memory. We can go ahead and go to sleep while it's doing that. When all of those inputs are done, the ones that we programmed, it will wake us up. Lowest possible software, lowest possible current, maximum benefit to your code.
In Lab 4, you'll write code to measure values using the on-chip 10-bit analog to digital converter. To keep things simple, you'll use the internal temperature sensor as an input to the ADC. You can then use your finger to warm the MSP430 on the LaunchPad board to see the temperature change. Starting out in Lab 4, Step 1, create a new project by clicking File, New, CCS Project. Make the selections as shown below. Remember, if you're using the 2231, make the appropriate choices for that part. Make sure to click Empty Project at the end. The location is the MSP430 LaunchPad Labs Lab 4 project. And when you're all done, click Finish. So we're going to start coding here. Most coding efforts make extensive use of the cut and paste technique, or lots of folks call it code reuse. The MSP430 family is probably more prone to the use of that technique than most other processors. There's an extensive library of code examples for all the devices in both assembly and C. So it's extremely likely that there's a piece of code somewhere which does something similar to what we need to do. Additionally, it helps that many of the peripherals in the MSP430 devices have been deliberately mapped into the same register locations. In this lab, we're going to reuse the code from the previous lab exercise, along with some code from the code libraries and demo examples. So let's open the files containing the code that we'll be using in the lab exercise. Open the two files using File, Open File. So let's open up in the Lab3 Files folder, opt under vlo.txt. And in the Lab2 Files folder, we want to open up the temperature sense demo.txt. Go ahead and copy all of the code in the opt under vlo.txt file and paste it into main.c, making sure you erase all the existing code in there. This sets up the clocks for us. We're going to have the A clock running on the VLO, and we're going to have the M clock running on the DCO over 8. So that's the 1 megahertz clock over 8, about 125 kilohertz. In step 3, we want to make sure that the SM clock, the submain clock, is also set up. So in the instruction where you see the basic clock control register 2 being ORed with the CELM 0 div 3, you want to add div S under 3. The SM clock default from reset is sourced by the DCO, and div S under 3 sets the SM clock divider to 8. So now the clock setup is the A clock is on the VLO, the M clock is on the DCO over 8, and the SM clock is on DCO over 8. Remember, if you're using the 2231, make the appropriate change to the header file at the top of the code. So as a test, let's go ahead and step 5, build, load, and run the code. So go ahead and run the code. If everything's working correctly, the green LED should blink very quickly, and I can see on the board that it's working properly. When you're done, halt the code and click the Terminate button to return to the editing perspective. Next, we're going to reuse the code from the temperature sense demo to set up the ADC. This demo code has the needed function for the setup. So in step 6 from the temperature sense demo text file, copy the first 4 lines of code from the configure ADC temp sensor function and paste it as the beginning of the while loop just above the P1 outline. Those lines of code are the one that controls the ADC10 control register 1, ADC10 control register 0, the delay cycles for 1000, and then the rewrite to the ADC10 control register 0. So let's examine those code lines one at a time to make sure they're doing what we need them to do. You'll need to open up your user's guide and header file for reference again. It might be easier to keep the header file open in the editor for reference. So first thing, let's change that ADC10 div under 3 to ADC10 div under 0. The ADC10 control register 1 is one of the ADC10 control registers. Inch under 10, that's input channel under 10, selects the internal temperature sensor input channel. ADC10 div under 0 selects divide by 1 as the ADC10 clock. Selection of the ADC10 clock is made in this register and can be the internal 5 megahertz oscillator, the A clock, the M clock, or the SM clock. The ADC10 oscillator is the default oscillator after the power up. So let's go ahead and use those settings. If you take a look at the ADC10 control 0 equals SREF1 and so on, the second line that we put in there, SREF1 selects the range from VSS to VREF. That's ideal for the temperature sensor. ADC10 SHT, the sample and hold time 3, has the maximum sample and hold time. Again, that's ideal for the temperature sensor. The ref on parameter turns the reference generator on. We're going to have to wait for the reference voltage to settle after this line. ADC10 on turns the peripheral on, and ADC10 IE turns on the ADC10 interrupt. We don't want interrupts in this lab exercise. We haven't covered interrupts yet. So go in there and change that line where it says ADC10 on, ADC IE. Go ahead and take ADC10 IE out of there. The next line allows time for the reference to settle. A delay loop is not the best way to do this, but for the purposes of the lab exercise, it's fine. We're using this delay cycles 1000. That's a lot longer. If you reference the user's guide, the settling time for the internal reference is something less than 30 microseconds. As you may recall, the M clock is running at DCO over 8, so that's 125 kilohertz. A value of 1,000 cycles is 8 milliseconds, which is way too long. A value of 5 would be 40. So let's go ahead and change that delay time to delay cycles 5. The next line enables the conversion, the ADC10 CTL0 enables the conversion and starts the process from software. According to the user's guide, we should allow 13 ADC10 clock cycles before we read the conversion result. 13 cycles of the 5 megahertz ADC10 clock is 2.6 microseconds. Even a single cycle of the DCO over 8 would be longer than that. So we'll leave the LED on and use the delay so that we can see this with our eyes. So leave the next two lines alone. That puts us in step 8. When the conversion is complete, the encoder and the reference need to be turned off. The encoder bit must be off in order to change the reference bit. So this is a two-step process. Add the following two lines right after the first delay cycles 100. And that's the ADC10 control 0 that's turning off the encoder, stopping the process, and turning off the reference and turning off the ADC. So that takes us to step 9. Now the result of the conversion can be read from the ADC10 memory. So next, add the following line to read this value to a temporary location. That's temp raw equals ADC10 mem. Remember, we're going to have to declare this temp raw variable right after the #endif line at the beginning of the code. So we're going to declare a volatile long temp raw. The volatile modifier forces the compiler to generate code that actually reads the ADC10 mem register and places it in temp raw. Since we're not doing anything with temp raw right now, the compiler optimizer could decide on its own to eliminate that line of code. The volatile modifier prevents that from happening. So in step 10, the last two lines of the while loop turn off the green LED and delay for the next reading of the temperature sensor. This time could be almost any value, but we'll use about 1 second in between readings. The M clock is DCO over 8, that's 125 kilohertz. Therefore, the delay needs to be about 125,000 cycles. So the P1 out equals 0 turns the LED off, and then the delay cycles delays for about 1 second. At this point, your code should look like the code that you see on the screen and the code that's in step 11 of the workbook. We've added some comments in the workbook to make it easier to read and understand. Go ahead and click the Save button on the menu bar to save the file. For reference, if you're having problems, you can find this code in the lab files in lab4.txt. Go ahead and close the opt.vlo.txt file and the temperature sense demo reference files. We don't need those anymore. In step 13, go ahead and click the debug button. The debug perspective should open, the program should load automatically, and you should now be at the start of main. Go ahead and run the code. If everything's working correctly, the green LED should be blinking about once per second. And we can see on the screen that the LED on the board is blinking about once per second. Go ahead and click Suspend to stop the code. Now we need to test the ADC10 conversion process and make sure that's actually working. In the code line containing temp raw equals ADC10 mem, double-click on temp raw to select it. Then right-click on it and select Add Watch Expression. Then click OK. If needed, click on the Expressions tab. You can give it a name, whatever name that you want, temp, that's correct. And then click on the Expressions tab to make sure you're looking in the Expressions window. Right-click on the next line of code, P1 out equals 0, and select Breakpoint, Code Composer Studio Breakpoint. When we run the code, it will hit the breakpoint and stop, which allows the variable to be read and updated in the watch window. In step 17, make sure the expressions window is still visible and run the code. It will quickly stop at the breakpoint and the temp raw value will be updated. So we have a value of 730. Let's go ahead and run it again. Run it a couple of times. The readings should be pretty stable here, although the lowest bit may toggle, and you'll see the value with a yellow in it like that. A typical reading is 734, 729, somewhere in there. Your reading may be different because your room may be hotter or colder. You can right-click on the variable in the watch window and change the format to hexadecimal if that's more interesting to you. As you run it, you can also put your finger on the part itself. Go ahead and run it again. And it's 729 now. Go ahead and run it again. 731. So it warmed up as my finger was on there. Just to the left of the P1 out equals 0 instruction, or on the instruction you set the breakpoint on, there's a symbol indicating that a breakpoint's been set. It might be a little hard to see with the program counter arrow in the way. Right-click on that and select Breakpoint Properties. We're having some difficulties with our capture tool here, so you can see, at this point, you'll see what those capture properties look like. We can change the behavior of the breakpoint so it will stop the code execution, update our watch expression, and resume execution automatically. Change the action parameter from remain halted to refresh all windows as shown below. And click OK. Now go ahead and run the code in step 19. Now the breakpoint occurs. The value in temp raw is shown in the expression window is updated without us having to do anything. Again, I'm going to reach up and put my finger on the part. And after a few seconds, we should see that the value in temp raw goes up. So now it's at 731, 733, 735, and so on. So that works fine. So you can see that the measured temperature climbs, confirming that the ADC conversion process is working and that your code is working the way that it should. Every time the variable value changes, Code Composer highlights it in yellow in the expressions window. Terminate the active debug session using the Terminate button. This will close the debugger and return Code Composer to the edit perspective. Then you can go ahead and close the project by right-clicking on Lab 4 in the Project Explorer pane and go ahead and close the project.